So let's proceed on those lines, pulling out the various terms. So to be a little careful here with our bookkeeping, but I think we can do this. So the first term, which is this classical term that I like, the quick way to see what it's going to give me is to simply rearrange the order of summation, because I'm always allowed to do that. So I could write this as sum on n, right? Rn hat times sum on m, p hat m, p hat m. And then, so I've taken care of this term. The next classical term, I think, also can be done very easily by rearranging my summations, right? That's sum on n, r hat n, p hat n, sum on m, r hat m, p hat m, like so. So I've taken care of this term. The remaining terms are the commutator terms, and those all come with an h bar over I. So let's factor that out. And the fact, by the way, that it has an h bar is a good indication it's a quantum term, because this term would vanish if h bar went to 0. So now in this first term, I'm going to have sum on n, right? I'm just rearranging the order of my terms. I took care of the h bar and I. I've got sum on n. I can get the piece that depends only on n. I now have to put in my sum on m for the other two pieces, which is going to give me my p hat m, and it of course has the Kronecker delta n m. Now, the next term, if we look at it, notice it's actually identical to the first term, right? The minus signs will cancel. And once they cancel, it's a plus sign, and it's the same h bar and I delta nm, and it's the same rnpm, just like I had over here. So this term is actually being produced twice. So I can just put a factor of 2. That was pretty ugly here, factor of 2. Then I've taken care of, therefore, this term and this term. This term was 0. I've only got one last term to go, which will be this term. So let me write that in. It comes in with a minus sign over here. Pulled out the h bar on I. I have sum on n, r hat n, p hat n, and then I'm left with sum on m here, right? I'm pulling my sum in. And then the last remaining piece of this term is just delta m m. And it looks like so. Okay, so now I think we are ready really to interpret this back in terms of a more normal vector language. So the first piece, notice this is just r dot r, right, applied after I apply the effects of p dot p, minus then, and this is really r dot p applied to the effects of applying r dot p. So that looks just like actually the classical term. The quantum mechanical pieces, we're going to do a little thinking on these first, but they definitely come with h bar on I. Let's look at this. In this case, this term, there are only two types of terms, right? There's n is different from m. So if n is different from m, I get 0. So all those terms I can ignore. When I should better put it this way. When I sum over m, only one term won't give me 0. That's actually the m equals n term. All the rest give me 0. And that term, the result of that term is just p hat n, because m will equal n for that term, and delta nn is just 1. But if you look what I have, I've got twice the sum rn times pn. So that is really just a factor of 2 multiplying this whole result here is going to give me then r dot p. That very definition. On this side, this sum also is just the definition of the all the r operators gathered into a vector and all the p operators gathered into a vector dotted with each other. And the last remaining piece is this term. Now delta mm is always 1, so I'm summing 1s. And I'm summing 1 once for the first term when m equals 1, and then I get another 1 when m equals 2. And then finally we live in 3 dimensions, so there will be 3 terms in the sum, and this term here gives me 3. So I have 2r dot p minus 3r dot p. So that's really just minus r dot p. R dot p. And as we've said, I've been pulling out my h bar on I. So this is a lot of progress. This is very much boiled down now. These are all operators, by the way. I'm apologizing. I had forgot my hats. Our next stage then in the analysis is to express now this operator expression directly in terms of our coordinates, because we have very simple expressions actually for the r operator and the p operator. So let's make that maneuver next as we boil this down. So now when I replace each of the components of r hat with the corresponding component of r and take the dot product with itself, that is just going to give me r squared. When I do p dotted with itself, that's going to be this dotted again with itself, which will give me, notice, 2 factors of h bar and 2 factors of 1 over I. So there's an overall minus h bar squared, which is going to appear quite commonly. So I'm going to factor that out. And then what's left is this del dot del, but we know del dot del is just the Laplacian, del squared. So that's the coordinate representation for these two operators. Next, I have to do minus. Notice again, I'm going to replace r with its coordinate vector, and p will be replaced with h bar and I times del. There are 2 p's here, so that again will pull out a minus h bar squared, and what I'm left with then are dels sitting in the places of the p's. So I have minus r dot del as the first operation, where these are now written in terms of the coordinates, and the second piece will also be r dot del. So those are those 2 bits. And now I'm also, I guess I should tell us what we're doing, because we're about to get a box around this. So this is L squared, and what I'm doing is I'm now using the coordinate rep of the operators to translate this down now just into mathematical language. So that was my first term, that was my second term. This term, once again, when I substitute in for p, there's going to be an h bar on I times this h bar on I will again give me minus h bar squared. There's still a minus sign, so there's still minus, and what I'm left with then is r dot, and what's left of p, because I did the h on I, is again just the del. So this r dot del operator appears to come up now over and over again. So I think we should give that a little bit of thought as we simplify this down. Note, when I do r dot del, back to our vector calculus, the r vector is just the distance from the origin r times the unit vector r hat dotted with del, right? And we're in our coordinate representation now, so we're just doing normal, a vector calculus. Now the unit vector, any unit vector dot del, gives me what's called the directional derivative. And the direction I need the derivative in is the r direction, so that r dot del is actually just d by d, the direction r. So we're in very good shape now, I think, to continue simplifying things a bit. This is going pretty well. So I have minus h bar squared r squared del squared minus, these 2 terms repeated will be r d by dr times r d by dr, and then minus r d by dr. Now, this last term and this one, notice I can combine in a very nice way that's going to start to look like my Laplacian operator. If we went all the way back to the beginning here, notice the Laplacian operator has a 1 over r, 2 derivatives with respect to r, and then an r, right? What I have here is almost that, but the I don't have a second derivative with respect to r. These are a little bit out of the order I would like. I would really like them in this order. so I can put back in, right, doing my commutator trick. That will give me d by d squared r of r. And the cost I've paid for that rearrangement is this commutator, but I hope you will recognize that this commutator is just -1 because it's a coordinate commuted with its derivative. It's the backwards version of the 1 that we always set equal to 1. And with this as a -1 factor, this term will become plus, and then it's subtracted from itself. So these two terms here will actually cancel. So this now really is my expression for L squared. And finally then, I can solve for the del squared operator because this is the thing that goes directly into my Hamiltonian. So let's solve for del squared. So therefore, I can write del squared as follows. Now, to solve this, I'm going to do a bit of the algebra here in my head, right? So the first thing what I'm going to do is I'm going to divide by h minus h bar squared. So I'll have L hat squared over h bar squared. And I'm going to do it also with this minus sign. So what that does is then gives me, that's L squared. I move this h bar squared onto the other side of the equation. And then I'm trying to isolate del squared, so I need to add then to both sides of my equation this particular term. So there's going to be plus r d by dr squared r. And that then is actually equal to r squared del squared. Now here is the last step. Notice, I'm just dealing now not with operators, but just with a normal coordinate representation. But I'm dealing, with the Laplacian operator here. If I want to just solve for what the Laplacian operator would be by itself, we of course can imagine that this is applied to some function. So it'd be r squared del squared on the function equals all this stuff applied to my function. If I wanted to solve that equation for just del squared by itself, or del squared on my function by itself, I would just divide both sides by r squared. So I would do a 1 over r squared times these pieces. Now the one thing we have to be careful of when I write this, and I'm trying to be very careful, is notice that I have to always imagine this del squared on f is this stuff here applied to f, these terms. Now, notice when I do this, when I divide by the r squared, it has to stay here on the left. I can't just move it on to the right because these operators are applying directly to whatever function I'm imagining I'm applying these operators to. So this then gives me really my expression for del squared. And let me rewrite this now in a nice, neater way. I certainly can combine these two terms, which will leave me then with 1 over r d by dr squared r, and that should be very exciting to us because that looks a lot like our Laplacian from up above, minus 1 over r squared times L hat squared over h bar squared. So that's one key result. I want to put a box around that one. So this del squared operator, which has all of this complication associated with it, we now have a much simpler expression for it in terms of the angular momentum. And that expression teaches us also something very important. Notice the first piece, the radial pieces, are exactly the same as what we have below. That tells me that the rest of this term must be what comes from the angular momentum. That remaining term must be these pieces. And notice that these pieces already have an r squared out in front of them. And what's left, these angular bits then, must just be minus L hat squared over h bar so that the final result lines up with what I have here. So the other conclusion we can draw from this is that the square of the angular momentum operator must be then these remaining pieces, L squared over h bar squared. So L squared will be minus h bar squared times just these angular parts. So it'll be minus h bar squared, and the angular parts had a 1 over sine squared theta times d by d phi squared, plus then this crazy beast, sine theta d by d theta sine theta d by d theta. So we also get out of this the angular expression for L squared. And I want you to notice that L squared operates only on the angles, theta and phi, not the radius. And that's a very useful algebraic fact we can exploit in our next step in our analysis.